All right, so we were working on that problem, sample problem 22. And we had the massive shield door at Lawrence Livermore Lab, which I believe is in Berkeley. And we had a force that was applied this way. We had a hinge or the axis of rotation up here. And we were told that the moment arm R was equal to what? 2.4 meters? Okay. And we know what the rotational inertia of the door is because that would be something that would be kind of hard to figure out. And then what were we trying to find? What does the problem say we're supposed to find? Okay, so we're supposed to find F applied. And I believe that I was trying very hard to pull teeth and get you to think about the last sentence of the problem, which talks about making the door move from rest through an angle of 90 degrees in 30 seconds. And what should that sound like? That should sound like a very familiar type of problem to you. Kind of like projectile motion, but I've only got one dimension. So what came before projectile motion? Yeah, chapter 2. Remember chapter 2? I always talk about them as chapter 2 problems. This is a chapter 2 problem. Okay? And what would I find doing my chapter 2 problem? What information am I looking for? So let's see what our knowns are. What's theta 0 going to be? Because it can be. What's theta going to be? 90 degrees, but do I want to leave it as 90 degrees? Pi over 2. Pi over 2 what, Maddie? Radians, right? Because if it's radians, I don't have to make it go away. Degrees I have to cancel because they're a real unit. What's omega 0? 0, because I'm starting from. Do I know what omega is? Do I know what T is? What's the thing that's missing from my list? So, of all my stuff here, which is the thing that I'm going to want to solve for on my side trip? Why? Okay, Okay, so I want to find alpha because I can use the acceleration somehow to find the force. So what's my equation here that I'm going to use to find alpha? Oh, I can do it that way. Good. Okay. And lucky for us, a bunch of stuff goes away. So I end up with theta is 1/2 alpha t squared. And then if I solve this, I get alpha is 2 theta over t squared. Is that right? I think if I do my algebra. So I've got 2 times pi over 2 radians divided by 30 seconds squared. And what do we get? And don't give it to me in terms of pi, give me a decimal. 0.0035 watts. Radians per second. Yeah, because it's an acceleration, and I squared my denominator. Okay. So I'm assuming this was a productive side trip, but how does this get me back to solving for F applied? Okay, so my applied force here is creating a torque on the door, okay, making it move. So I can say that tau applied, what did you say it was though? It's I alpha. But where do I get my F applied in here? What else is torque equal to? Okay. What's R? It's not just radius, actually it has a different name. It's okay, well let's go. It's the distance from the axis of rotation to where? It's the moment arm. So it's the distance between the axis of rotation to, no, to where the force is applied, which is often the radius, but not necessarily. And then what's phi? Okay. So what's phi if it's the angle between the force and the moment arm? 90 degrees. And sine of 90 is 1. Okay. I always get nervous. So this tells me that F applied is equal to I alpha over R. You can substitute the numbers in and tell me what F applied is. How many sig figs do I have running around this problem? So what should it be? Do you agree, Sari? Okay. All right, you got it. Okay. All right, so this was kind of a plug and chug, but it brought together a lot of different formulas that we have used. Okay. All right. So let's take a blast from our past and go back to a situation where we actually used something that rotated, but we ignored it. So let's go back to Atwood's machine. And when we talked about Atwood's machine back in chapters 5 or 6, we treated a pulley, which is a round object that rotates, as something that just changed the direction of the force. And we considered our pulleys to be massless and frictionless, and we ignored them. But now we don't have to anymore. Well, so I've got my pulley. I've got my masses that are going to go around my pulley. M1, M2. Now, instead of ignoring my pulley, I'm going to tell you my pulley has a radius R, and that my pulley has a rotational inertia I, It doesn't really matter, oops, what it is. We're just kind of going to do some general equations and look at some stuff. Okay. Don't know what to tell you. Okay. So if I was going to solve this problem and look at what the acceleration of the system was, what would I do first? Free body diagrams, but now it's not just M1 and M2, it's also for the pulley. Okay, so I've got my M1 here. There's going to be FG1 going down. There's going to be tension 1 going up. If I consider the pulley as a part of the system, I can't assume that the tensions are the same on both sides anymore. I've got my M2. And again, I'm going to have FG2 going down, tension T2 going up. Not necessarily. And then I have my pulley with some rotational inertia I. And what do I draw on the pulley? This is a free body diagram. What do I draw in free body diagrams? Forces. So what forces are acting on the pulley? Yes. Hang on. We tend, if the pulley is fixed, then that means that at the center of mass, that's how it's fixed. Okay, and it's not only the center of mass, it's the axis of rotation. So if there's something that's, a pole or something that's going through the center of the pulley to hold it in place, that force is acting at the axis of rotation. So what's the moment arm? There isn't a moment arm. The moment arm is going to be equal to 0, which means that I don't have to worry about that force because it's not going to exert a torque, which is really what I'm going to care about. Okay? And the gravitational force is also going to act at the center of mass, which for a uniform, well-balanced pulley is at the rotational axis. So I don't have to worry about the gravitational force either. What are the forces that are going to be relevant here that are going to introduce torques, which is what I care about? The two tensions. So I'm going to have tension 1 going this way and tension 2 going that way. And that's really going to be it. Everything else is going to act on the axis of rotation. Okay. Now, what's missing from my free body diagrams here? Nope. Direction. Now, you remember, I hope, that you have to have the same direction of motion to be positive for M1 and M2, okay? But remember, now I've got something that rotates. And so which direction has to be positive for the pulley? Counterclockwise. So this direction has to be positive for the pulley, which means that that direction has to be positive for M1, and this direction has to be positive for M2. So that when everything moves this way, everything is moving in the positive direction. Okay, which is really the key to dealing with an Atwood's machine or anything that involves a pulley, is that everything's moving in the same SIGN sign direction. Sari. Because I said so. I mean, it's really that simple. It's counterclockwise because the book says that everybody agrees that counterclockwise is positive. Could you start a revolution and have counterclockwise be negative? Yes. But you would cause a lot of work for a lot of other people who assume it's positive. When you reinvent science after the zombie apocalypse, you may make it whatever you like. Okay? All right. So I've got my direction. Now what do? I don't really have any notes. What do? I've got my free body diagrams. Now what? F net equals MA. Okay. So I've got F net equals M1A. I'm going to call it A1. So for F net, I'm going to have M1G minus T1 is going to be M1A1. Okay, you know how to use a free body diagram now. You know how to use F net equals MA, so I'm going to be cutting corners here. All right. If I do F net equals M2A2, then that's going to give me T2 minus M2G is going to be M2A2. And then for the pulley, I'm going to use tau net. And what's tau net equal to? I alpha. Okay. It's a vector in the sense that it can be positive or negative, but it's not truly a vector yet. That will be the next chapter. We will make tau into a true vector, but it involves some math that we don't know how to do yet. You don't know how to do yet. So, as a little aside up here, how do I figure out what a torque is? What's the formula for torque? Gianni, since you're already looking. R. I don't want I alpha. I want to actually find the torque itself. Yep, RF sine phi. Okay. So that's how I'm going to figure out the torque that's coming from T1 and the torque that's coming from T2. Okay. I don't know if I can get it all on there. So my torque that comes from T1, is that going to be a positive torque or a negative torque? Pretend it's a string and pull it. Which way does it make the pulley go, positive or negative? Positive, right? I pull it, it's going to move it this way. Okay, so T1 is going to be positive. It's acting out here a distance from the rotational axis. So what's my moment arm going to be? Capital R, the radius of the pulley. So I'm going to have RT1. And what's the angle between my moment arm and my force? 90 degrees, and the sine of 90 degrees is 1. Okay. You all get it wrong enough that I still reserve the right to cringe before I ask you. Yeah. Yeah. Let's only talk for ourselves here. All right, T2. Is T2 going to produce a positive torque or a negative torque? A negative torque. So it's going to be negative. What's the moment arm going to be? R. And again, what's the angle between the moment arm and the force? 90. And the sine of 90 is still 1. So that's going to give me I alpha. Okay, so I got a lot of stuff up here. Now, if you remember, hey, I want to know the acceleration of the system. That's almost always what I want to find in an Atwood's machine. Now, you may recall from when we did the Atwood's machine originally in class that we were able to say something about the accelerations. When we talked about the acceleration of mass 1 and mass 2, what did we say? They had to be what? They had to be equal. Their magnitudes at least, because I had one string connecting both masses, and if the string remained taut, straight, T-A-U-T, taut, then everything had to move with the same acceleration because it was all connected, just like the whole thing has the same velocity. Should we care to figure out what that is? So I can say that A1 equals A2 equals A, but what am I going to do about alpha? Well, A and alpha aren't equal to each other. That's not true. Come on, Sari's going to give us the answer in a minute. She's putting it together in her head. I can see it. Don't stare at her, Gianni. No pressure. Others can help too, but what does the alpha mean? So the alpha is whether it's speeding up or slowing down, right? So it's related to which acceleration? It's related to the chapter 2 acceleration, right? And what's that relationship between alpha and the chapter 2 acceleration? Okay. So we could say that alpha was equal to, well, then you should have said it out loud. Okay, then alpha is going to be equal to that chapter 2 acceleration, which is the same as this, divided by r, which is the radius of my pulley. Okay, we doing all right? You with me? So we can rewrite these equations a little bit and make them a little bit simpler. So this one is going to be mg, in fact, I'm just going to solve this for t, minus m1a is equal to t1. I'm going to solve this one for t2 is going to be m2a plus m2g. And this one I'm just going to rewrite as, I'm going to divide both sides by r is what I'm going to do. So I'm going to have t1 minus t2 is going to be I a over r squared. Multiple steps here. Okay, you with me? All right. So what I'm going to do is substitute in for T1 and T2 in that equation. And then everything that I have will just be a function of the masses, the rotational inertia, the radius of the pulley, which are all things that I know, and my only unknown is A. Omniscient narrator. It's a good thing. So my formula is T1 minus T2 is I A over R squared. And there's a reason why we write it that way too. So T1 is M1G minus M1A. T2, I'm going to have a negative sign in front of everything. And I move the R squared to under the I for a reason. Multiplying by R squared really won't get us where we want to go. I mean, you could, but it's not really going to help. I'm going to get all my A's on this side. So I've got M1G minus M2G is going to be A times I over R squared plus M1 plus M2. And then A is going to be M1G minus M2G over I over R squared plus M1 plus M2. Which should look suspiciously like what we had for acceleration when we figured it out, except that this term was missing, right? If I block that off, then what I have is M1 minus M2 over M1 plus M2 all times G, okay? And so I ask you then, what effect does the pulley, if we don't ignore the pulley, if we consider the contribution of the pulley, what should happen to the acceleration that you measure, as opposed to ignoring the pulley? 5 or 6. But if I add some, Maddie. Sure. I move these over to the other side and then factored out an A. Because I would add M1A to this side and add it to that side. Oh, okay. Oh, all right. There you go. Okay. So what am I doing to the denominator here? If I don't let I be equal to 0. I'm making it bigger. So if the denominator gets bigger, what has to happen to my acceleration? It gets smaller. So if what you did in your experiment, because remember when we did the lab, you calculated what the acceleration should be. for each combination of M1 and M2. Okay? If you did that, then what you calculated should have been consistently bigger than what you measured because your pulley really did have a rotational inertia. Okay? So friction as well, but you're not accounting for making the energy, what's necessary to make the pulley turn. Okay? I want to make one more point and then I'm going to let you go because I'm not going to start the next thing if we don't have class tomorrow. I wrote this as I over R squared because, for instance, the rotational inertia for a disk is 1/2 mr squared. And then those R squareds would cancel and then we just have something up here that would be like 1/2 m. Okay? So that be it. Don't worry about getting the homework done for Thursday, but I would work on the homework. We will make it be due on Wednesday, and that is when the quiz is as well. Okay?